Today we are going to talk about the PCA, the principal component analysis and factor analysis. So Anna is going to present for us this chapter. And thank you, Anna, for taking part of this book club and discussing the chapter for us. And the floor is yours.
So I was starting by saying that I joined this book club because I am feeling overwhelmed about the amount of new information and formulas, mathematical formulas that are happening every day in the classes. So I volunteered to present this chapter, but I'm not an expert on the matter. Afshin is, and I struggled a lot in this part. So whenever I say something wrong, please Afshin correct me. So this first part of this chapter, which is about dimension reduction methods and reasons for dimension reduction, starts precisely with these reasons. Why do we need to reduce the dimension? And I found in this text 5 main reasons to reduce the dimension. One of them is multicollinearity, which is almost the same as the covariance of certain variables that can lead us to wrong results. Like, for example, if we put correlated variables in the same model, certain predictors can appear as significant overall, even in the case that they are not significant by themselves. This is one problem with the correlation between the variables, and the other problem is the instability that occurs if we, this maybe will not call instability, but the inclusion of variables that represent the same, they can double the weight of a certain component of the model, as we have talked in class. The second problem is that the higher the dimension, the sparser the results are. So we have fewer important or precise results. And also, if we have too much variables, the number of the size of the function will exponentially get bigger, and it will not be tractable in terms of computing or understanding for us. So also another reason to reduce the dimension is that too many variables can complicate the interpretation of the analysis and will violate the principle of parsimony. So I didn't know what this was because I don't use it every day. The principle of parsimony is that states that the most acceptable explanation for an occurrence, phenomenon, or event is the simplest, involving the fewer entities, assumption, or changes. This is also best for a simpler interpretation, of course. Also, if we include too many variables, we can overfit the module, as we have seen this concept during classes. If we overfit, we will get good fitting with training data, but then we will have no good results with the new data that we insert in the model. Another reason to make this dimension reduction is that several predictors, so several variables, might fall into a single factor or component that addresses the one single aspect of the data. And this is already in the other page. And lastly, full dimensionality of a problem. We cannot deal with it with the formulas and the computing. because the most advanced models in terms of data visualization don't go beyond 5 dimensions. So I hope you have understood this part. If you don't, please put your questions. And for the dimension reduction methods, we use the correlation among the several predictors. And the goal of using this correlation is to reduce the number of variables or predictors in the model. It's to ensure that the predictors are independent, because if they are not, it could happen those problems that I told you in the beginning, and also to allow better interpretability of the results that we get from the model. The models that we are going to cover in this session are the PCA, and the main part of this chapter is about PCA. So principal components analysis. Also, Afshin is going to talk about factor analysis and user-defined composites, but the major part of it and the base of it all, even the factor analysis, is the PCA. So the PCA, it requires a matrix algebra domain. I don't know about you, but I have done this many years ago, and I was not bad at it. But when you don't use it every day, you start forgetting. And so I skipped this part totally, as they recommend in the book, and I went directly to the results. Okay, and so in the results, one thing I noticed, and then I struggled a little bit with this, so I think it's best, I understand it now, but I think it's best Afshin explain it, the results and also the examples. Can you please, Afshin?
Yes, okay.
Thank you.
All right, so about this principle of parsimony that you told us is very important in using this method. It is mostly about this matter that the information that we use and the data that we use is very important, because this is a part of our asset. And if we want to make a good model, we have to use the best from the data that we have. This data that is a kind of asset, if we use it in a wrong way, we are losing the information. And the information is something that is important for us. The number of the variables that we put in our model needs more data to use in the train part of our model. And because of that, the amount of the data that we lose to import one variable in our model make some cost for our model. And this is the reason that we said that the number of the variables should be controlled, and we have to use the variables that they are really useful for our model. So we call this the principle of parsimony. It means that we have to use the variables in our model that they are really useful for our model. They put some extra information, and we can use them to empower our model. So we remove the redundant variables because of this principle of parsimony. And here the principal components can help us, the PCA can help us to do it, to make a combination of the variables that these new variables that we have, that we call them the components. These components are completely independent, and by this we can somehow remove the redundancy in our data. So this is the main goal of the PCA. So here in result 1, it said that the principal component is working when we make our variables standard. So we have to use some standardized methods, like, for example, subtracting the mean of the population and dividing to the standard deviation to make the data somehow standard. Okay, and based on these standard values that we call them, for example, the Z here, we do some calculation to find some values for these variables and to analyze the correlation of these variables to find out a way to combine them in a proper way, okay? Make some factors, make some new variables based on the variables that we have, based on the combination of them, and then we use them as the principal components in our model. These kind of principal components are coming from these calculations that we have here. Here we can see that the summation of the variances of the z's are equal to the summation of lambdas, and it's equal to the number of the variables. It means that the variance of the z here, because it's the standard value, all the variances are 1. And if we make a summation over I from 1 to m, then the result would be m. And here, if we go to the example, so here we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 variables. And here we have the total. So this total is the lambda that we had in that formula. And if we make a summation of these values, you can see the summation of these values would be 8. Okay, so that is the idea that the summation of the variances of the z's are equal to the summation of lambdas, and this is the lambdas that we have here and the eigenvalues that we have, and if we make a summation of these, we will get this 8. That is the number of the variables that we have. Okay, so this is the theorem 1, or that part 1 that is mentioned in that page of the book. The result 2 is about this idea that the correlation is something that the principal component is working on. So when we want to combine the different variables, we do it by calculating the correlation of the variables. Okay, and by the correlation of the variables, we will find the variables that they are close to each other, and then we combine them as a principal component. So the components are coming from the combinations of the variables based on how they are close to each other and how they are related to each other. And this correlation is related to the eigenvalues, as we can see here. And it is going to tell us this idea that if we can calculate the eigenvalues and we somehow, based on the correlation matrix, we can have the eigenvalues and make some calculation on the eigenvalues, then we have some idea about the correlations of the different variables, and then we can manage them to make some principal components. Yeah.
Okay. And the third result, it's I think it's the simpler. It says that the proportion of the total variability in Z is explained by the eigenvector of the component. So it means that I will show you. Sorry. In this example here that I'm going to see from the beginning, because I think it's very useful. If you want to turn these eigenvalues into percentage of variance that explains the variability, you just have to divide this number, for example, by 8, and it will give you the percentage of variable. Okay, so is it right? Okay. So this example is very good because it puts into practice the theory that we have seen before. So we have a model in which the response variable or target variable, as we call it in the class, is the mean value of the houses. Okay, and these are the predictors or the variables that we have at our that we have available to explain and to create a model. But they are too many, as you can see, and we are going to try to reduce it. A bigger part for training and a smaller part for testing later. And it is also included in this chapter, the test part. So we see here the description of the variables, so the response variable and all the predictors, as we see that it's shown in the SAJ, for example. And then we have a sample of the data, and it is explained that x1, x2 until x8 are the predictors that we have. But we are going to try to reduce this amount of predictors. So we have a matrix that has the same variables horizontally and vertically, and that shows in a scatter plots the correlation between them. And this is a way to see it. It's a visual way to see, for example, that the number of rooms and the number of bedrooms are positively correlated, and that the latitude and longitude are negatively correlated. But I believe this is not the best way to choose the variables. So we have here the correlations. Sorry. We have here the correlations. And here, so this is variables, two variables. And here there is the correlation between the variables and the components that we found through PCA and through the matrix algebra calculations. That, as Afshin told me, they are not important for us to know in detail. It's just important for us to understand these values. So these values means that we have first, we have one component for each variable, and we are not going to choose to retain all the components, because we are only staying with the components that have a greater eigenvalue. So the eigenvalue is this value here in this table, and it is explained, the relationship between each component and the variables is this value here. And if this value is close enough to 1, it means that it has a positive and one-to-one relationship with the components. So here we have 4 variables that are related almost in the same amount inside the first component. And we have also a variable that has a negative correlation to this component. So we are going to stick with this to analyze further. Here in the second component, we see that the second component is more related to the latitude and longitude that are inversely related one to each other and also to the component. And the third component is explained mainly by the mean income, which is the first variable, and a little bit to the house age, which is the second variable. So the house age is negatively correlated to the first component and the second component, but not directly, because it has only a weight of 0.4. And finally, because we are not going to look at all of these, and I show you why, because they have no values that are high enough, all these values, for us to take these components into consideration in this method. So the last component that we will look at is one that is more correlated positively, but not totally, to the house age, and also a little bit to the mean income. So we are going to take these and see them in this chart and understand that with using the third result, this counts for 48% of the variance, and one question is that with PCA, the first component is always the one that is the most important, right, Afshin? Okay. And yes, followed by the second and the third. So it is calculated automatically, let's say, by Saj, but you need to know that the order is important. And the order is decreasing from the first to the latest. Depending on the model and the variables, we reach a certain point that almost the variability, almost all the variability is explained by a little amount of components, and that's our goal. It's to reduce. So from here down, we only have 4% of these components that explain the variability, so they can be dismissed for the model. Okay, so this is just the practical explanation of the...
There is a point here,
Yes.
Anna, that for this 4% that we are losing the information, maybe we consider this 4% of variability as an amount of information that we are losing because we are not considering the component 5, 6, 7, 8. But that is not exactly right, because in the data we have noise, and the components that they are not correlated with the variables that they are included in our components, mostly they are noisy part of the data. So that 4% that we are losing based on the variance is not totally the informative part of the data. They include also the noise, and most of the noise are communicated here in this part of the components that we are not considering. So don't consider this 4% as the amount of the information that you are losing based on PCA. It is less than that, because most of this 4% is noise, and maybe 2% of the information is there that we are losing because of the PCA, and we are paying this cost because we want to have the better model, and we want to obey that principle of parsimony. Okay.
Okay, thank you. So here I was also seeing that this phrase here, which is important, that with just one explanatory component, we can explain almost 50% of the variability. And remembering this one component, the first one includes already 4 variables. So here we have done a lot for dimension reduction. This is the way to rank and to analyze the component and to reach the components, to order them, and to explain how are they built. This is how are they built. They are built based on these variables that are more related to them. Okay, so then we have another question, which is how many components should we extract? And for this, we have a lot of questions, and we have some criteria that we can use on. First is the Eigenvalue criterion. The second is the proportion of covariance explained criterion, and minimum communality criterion and script plot criterion. They are almost all of them related to the PCA values. So the Eigenvalue criterion states that only components with eigenvalues greater than 1 should be retained. And here is an important thing for you when you for us when we apply it in practice. It means that if we are dealing with less than 20 variables, which is the case of this example, the eigenvalue tends to recommend the extraction of fewer components maybe that we need. And if we have more than 50 variables, it will outstand maybe too many components, so more components that we can deal with. Okay, so the component 4, using this criteria, component 4 doesn't reach this value of 1, so we should discard it. But because the number of variables it's so few, maybe we should keep it at hand and maybe stick with it because it's almost the value of 1. It's 0.825.
And Anna, it's not only because the number of the variables in our model would be very a small number of variables, but also it is about the closeness of this number to 1. So
Okay.
when even if the number of the variables is enough, if you have something, some components or some variable with very close to 1 from the eigenvalue point of
Yes.
view, it's better to keep it. It's better to keep it and test it with other criteria. So we have some other criteria. We check all of them to see if this one that is very close to 1 but is lower than 1 is worthy enough to be included or no.
Okay.
Because these are the information. Each variable that we are losing, if each component that we are going to put it aside, means that a little bit of information is lost from the model, right?
Okay.
And we have to have a good reason for that.
Okay. Yes. So next we will see the proportion of very explained criteria. This is just first choosing how much of variability that we want to explain, and then cut off the components by that value. And I will go to the example again. And for example, if you want to explain 85%, we will cut off here at number 3, and we will leave number 4 out. But if we want to cut off proportion of 95%, we need to include variable number 4. So with this criteria, the keeping or leaving component number 4 depends on the value of variability that you choose, a higher or lower variability. And in the book, it is explained about this, that it depends on the field of study. So if you are dealing with social sciences, for example, you can settle with a lower variability because you know that the human response is not predictable or precise like the science numbers. I don't know if you understand this, but if you are dealing with science, usually you go to higher variability to choose the number of components. Another factor is the purpose that you for what you use these components. If you are going to do the PCA only to describe the model, you can stick with a lower proportion and so less components. But if you are going to input these components into your model to make inference or to predict, like we are doing in this class, maybe it's best if you search for higher variability, and then you should include more components. The minimum commonality criterion is put here in between of these two criterions, but it's going to be explained lately because it's based on a different calculation. And the scree plot, it is very intuitive, and it's also given to us directly by Saj, which is a plot, a graph that has in the y-axis the number of the value of the eigenvalue, and in the x-axis the component number. And what it says is that when you reach an horizontal line or almost horizontal line, you need to exclude these components because they are not explaining many of the variability. So it's the same principle as we have seen before, but it's only shown in a different way with the scree plot. I think there's, one question is that if the curve is too smooth, maybe it's hard to understand where the line gets horizontal, which is not the case in this example.
And if so, we use the other criterion to, yes.
Okay. Okay, so in this case, this criteria tells us to include number 4 as well, because it's not, there is a big variability from the 4th to the 5th, from the 3rd to the 4th. Yes. Okay. So this is the summary of the criteria so far, which not include the communalities so far. But so far we have seen that by the eigenvalue criteria, we should put component 4 aside for now because it doesn't reach the value of 1. And the proportion of the variance explained criterion, as I said before, it depends on the value that you want to settle as an analyst. If you want to settle for 86, you'll get 3 components. If you want to reach 96% of variability, you should include number 4, component number 4. And the scree plot tells you that you should not go, you should not choose more than 4 components. So we are still in doubt for what to choose. Which is best, 3, 4? So the data miner analyst must weight all the factors involved in the decision and apply his or her judgment and tempered by experience. So here is the part of the human ability to understand which are the components and realize if it should include or not the 4th one. So component matrix. Okay. So Afshin, please, can you explain this part because it's not that easy for me. These 2 tables, please.
Yeah, so here we want to see that if you have to choose the 3 components or the 4th component, and what is the difference between these 2, if we choose 3 or 4. And here we can see that in component matrix 1, there is the relation between the correlation between the variables and the components. So for component 1, we can see that with these 4, the room size, and this one, the population, and this, the households. With the component 1, we have high correlation, but with this one, we have negative low correlation. So it is less than minus 0.5. And here we can see that for the component 2 is mostly related to the geographical part of the house. So it's mostly related to the address. So here we have the longitude and latitude. It is higher than 0.5. And for the 3rd one, we have only this one, the first one, that is greater than 0.5. And we can see that here we are losing the age, okay? Because component 3 is mostly related to the variable number 1. The component 2 is mostly related to latitude and longitude, and the first one is mostly related to room, bed, population, number of households. So we are losing somehow the variable 2, the age of the houses. And what if we consider the component number 4? In table 4 for B, we can see that component number 4 is mostly related to the age. And if we consider component number 4, it means that we are considering the age of the house. If we lose it, it means that the age of the house is not very important for us. So it depends to the literature of the study that if the age is important or no. Okay, so the analyst, if he decides that the age is not very important, he can remove the component number 4 and keep only the 3 first components. But if he considers that age is something very important and he wants it to be in the analysis and there is some interpretation at the end based on this age, so he should keep the component number 4 to be a representative for the age. Okay, so this is the idea for this part of the book.
Okay.
How can we decide if component number 4 is or not important? So it is from the by applying this model to new data?
This is mostly based on the experience of the analyst. So if the people that they define the problem, if they find out that based on the literature review, this is not a very important variable. This is a variable that it can help. It might be related to the problem, but mainly we don't have any evidence or very strong evidence that this variable is completely related to the problem that we want to solve it. Okay, in this case, they can remove it. They can say that, okay, we don't have any evidence from the literature review that this variable is completely essential for our analysis, and we can remove it. But sometimes the age is something that is very important. For example, in some studies of the health, they know that the age is playing a main role in this disease that they are studying. And based on that, they say that, no, we cannot remove it because this is basically one of the important variables and we want to have it because at the end of the day, when the model is working, we want to make some interpretation about the age of the people, right? So this is completely based on the ideas and the information of the people, the knowledge of the people, or the literature review that they did before, or the definition of the problem in their plan.
So
does it make sense?
Yeah, thanks.
Okay.
Okay.
So after that, we are profiling the principal components that we have chosen or that we have in doubt. So we are including here the number 4 and describing them to the client or to the person to whom we are building this model. So the first component, we can call it size component. And we say that it is largely composed of the block group size type variables. So all these variables are related to size and they are not the same, but it's logic that they will vary in the same way. So the total of rooms, the total of bedrooms, population and households. And at this point, we say that it includes median, housing age, counterweight, so a small part that counts negatively for this component. At this time, so far, we are still including this effect on this component. The second component, we call it geographical component, which is composed by latitude and longitude that, as I understood, correct me if I'm wrong, it is negatively related and all of this has to do with the shape of the state of California, right? Because the location of the houses need to be coherent with the space that we have available for them, right?
Yeah, so this negative correlation doesn't mean anything because it's only about the nature of the longitude and yes. So this is something, latitude and longitude. They are somehow correlated to each other. If the city is starting from, for example, northeast to the southwest, it would be different if it started from northwest to the southeast. And the correlation for the first one would be, for example, positive, for the second one would be negative. And that is only because of the nature of these two variables. So it doesn't mean anything, the negative or positive part of that. The only thing that is important here is component is related to the geographical part. So it gives us some information about the place of the houses that we are talking about.
Okay, then we have the third component, which definitively so far we have seen that we are going to include, which is mainly driven by median income of the block group, and it has a small effect of house median age in the opposite direction, as we have seen. And this component has eigenvalue greater than 1, so for all criteria so far we are going to included. This one is the one that we are in doubt, is the income and age, but it is more driven by the house median and age, and has a smaller effect of the variable of median income. So now we are going to investigate the relationship between principal components 3 and 4, and how are they constitute, and for that we use factor scores to estimate the values of the factors of each observation that we will see next. Okay, so this matrix here shows the relationship between the two variables that compose component number 3 and the two variables that compose the component number 4. As we have seen before, this is mainly about median income with a little effect of house median age, and this is the inverse. And here we see that there is a strong relationship between the median outcome and component number 3, and it seems to have no relationship, the house median age and component number 3. I don't know if you understand these matrices. I think they are intuitive.
I'm not understanding the graphs, sorry.
Okay, so I think I can explain. Here you have median income, housing median age, and component number 3. And these...
which one is the x and the y axis?
This is a matrix, so it's like columns and rows. In rows, you have median income, median house age, and component number 3.
Okay.
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 Okay, so this third line is composed by these two mainly and other variables. And here is the same. You have median income, housing median age, and component number 3. This is why the diagonal is not filling, because the correlation is 1.
Yeah, correct.
Okay, so you can see that median income and the component number 3 are almost overlapped. So it means that the most effect, the main effect in component number 3 and directly proportional is median income. But when you see the relationship between the component number 3 and house median age, it has no sense of correlation, visually talking. And the same happens when you look at component number 4, where median income and component 4 scores seems to have no visual correlation. But when you go to check housing median age and component number 4, they also have a strong relationship. Not that directly as component number 1, but also a positive correlation. Okay? So in this, okay, so now we are going to look at the magnitudes which are here in this table. The magnitude of the importance of each variable in each component. And we are going to see that according to the graph and according to this table, we should settle a value of 0.5 to exclude these variables from the components. Exclude in the explanation, because they are not going to be totally excluded from the components. They are not just going to be used to explain how the component was created and what is driven the component. Was I clear? I don't know.
Yes. So here we know that the component number 1 includes the age, the number of the rooms, the number of the bedrooms, the number of the population, and the households. Okay. So the component number 1 included these 5 variables. But the first one, that is less than 0.5, it means that this variable is not completely discussed with the component number 1. So component number 1 is not a good representative for this variable. And for component number 3, the age also is not represented with the component. And for the component number 4, the income is not representing by the component number 4, okay? Because the number is less than 0.5. So 0.5 is a threshold. And from this, what we include, we said that, okay, the age is not discussed with component number 1. The component number 3 is not a good representative for age, and it is not included at all in component number 2. So if we consider only component number 1, 2, and 3 in our model, we are losing the information about age. And again, if age is important for us, we have to keep component number 4, that the value is over 0.5 for component number 4, and age it is 0.806, right? So if we want to keep age in our model, we have to consider component number 4. If we don't care about age, then we can remove component number 4 from our model.
Okay, so continuing, we go from these tables with that threshold of 0.5. We go to this table here, where the values that were not sufficiently correlated to the components, as you see in this graph, they were excluded. So this also changes the definition that we are going to choose for the components. So here you see the part of the house age has been excluded in this definition. The geographical component stays the same because we were not in doubt about any variable. Income is also exclusively explained by median income, and housing median age by house median age, meaning that we are not counting the smaller effect that one has to the other in each component. So, Afshin, just one question from me. I know that I have asked this before, but for me, the suppression that we make of these variables inside the component, it's just in definition, right? Because in reality, they are not going to change anything with the numbers of the component.
No, they are not going to do anything with the number of components.
We
So
are just,
here we are talking about mutually exclusive components. The mutually exclusive components means that kind of combination of components that they are not related to each other, so they are completely independent, and they cover all the variables that we want to have in our study. So they have a good coverage, and they are completely independent. Okay, and I want to mention something here that might be important. What is the correlation? The correlation is the redundant information, right? So if we have from the explanatory variables, we have some correlation between the explanatory variables, it means that we have some redundant information. So we want to have some explanatory variables here, factors or components, that they are completely independent. And principal components analysis recommend us some components that they have these characteristics. And because of that, it can help us to have some variables in our model that they are completely independent and they are informative, and we have a good coverage of all variables that we had basically in our model. So we can say that they are mutually exclusive, and this mutually exclusive characteristic is very good for our components if we can get to it. And all of these analyses that we did till now, and Anna described them very well, are related to this matter, that we want to get to a point that we have some principles, we have some components, that they are describing the whole variables that we have in our model, but they are independent.
okay. So I just like to highlight this sentence here, because here you can see that the number of variables inside each component, it's very approximate to the eigenvalue of the components. This is one result of the PCA that we have seen. I didn't know if you have noticed this before, that 3.9 relates to 4 variables inside component 1, 1.9 to 2 variables inside component 2, longitude and latitude. And here 1, it's a little bit above 1, and it's related to 1 variable, which is income, and 0, 8 to 5 to another variable, which is 1. So here we have all the same 8 variables, but only with 4 components that will be part of our model. Okay, so the commonalities, it's important to explain another criteria, and the definition of commonality is the proportion of variance of particular variable that is shared with other variables. So it's the, may we say, redundancy and correlation that exists among variables. So the commonalities represent the overall importance of each of the variables in the PCA as a whole. So this is all related to PCA. Commonality values are calculated as the sum of square component weights of a given variable. And here we have an example. For example, that commonality of house median age that appears with the weight of with these weights in 3 components is 0.35 more or less, and the commonality with housing median age that appears in 4 components, it's almost 99%. So the commonalities that are less than 0.5, which you can see is the case of housing median age, can be considered to be low, and this will mean that the variables share less than half of its variability in common with the other variables. and this leads to that if we want to keep this variable in analysis, we would need to extract the fourth component. This is what Afshin has told before, which leads to the communality of house median age over a 50% threshold. So house median age only has a communality high enough if you have the fourth component. Okay, this is more or less the same, but with a different formula that is called the communality. And the minimum communality criteria, it's just saying that if you want to keep a certain set of variables in the analysis, then you need to have enough components so that you can have commonalities for each of these variables that is more than 50%. I think that Afshin have explained this before, in other words. So do you have any doubts about this criteria or not?
No, I think it went straight to the point.
Yes, thank you.
Yes.
So we are going to see, to resume all over again, all the criteria. So according to eigenvalue criteria, it recommends 3 components, but it doesn't reject absolutely the fourth. The proportion depends on what we want to do and what is our field of study. So we are doing prediction. And these values are not dependent on human response. I think they are a fact. So we are going for a higher proportion, and this criteria with 96% of variability asks us to stay with the 4 components. And the scree plot criteria also advises not to exceed 4, which is not contrary to the other 2. So the minimum communality criteria state that if we want to keep, like with our expertise and what we have learned in literature, if you want to keep this variable in the model, we should include the 4th component. Okay. So now we are going to validate the principal components that we have chosen. And in order to validate these components, we are going to perform the PCA on the rest of the data that we have put aside for test. And so the result component matrix is shown in this table with component weights smaller than 0.5 suppressed, like we did before. So they are not showing here. So the values are not the same because the data set is not the same, but we can see that the values are close enough to 1 so that we can consider them to be valid for our model. So this is what I was saying. So we may consider that the PCA validation was performed well. Now, this is another scenario. If we had done this test with the data set for test and the values appeared much different, that will mean this paragraph here, that then the analyst should take this as an indication that the values of the data set as a whole cannot be generalized, and the results should not be reported as valid. If we don't have validation from a subset of variables, then we may consider omitting these variables and performing PCA again. So I believe that Gonçalo asked before if we have to test the 4 components, and I believe the answer is yes. Right, Afshin? Even with business knowledge, if we choose 4 components and then this value drops very much, then the data set does not confirm our literature, for example. Is that right?
Exactly. So we have to go back to our literature review. If the model suggests us some changes in the basic model that we had from literature review, then we have to go back to the literature review and try to find some evidence for that. Because the data is not approving our basic model that it was our basic idea based on the literature review that we did, or based on the knowledge that we have from the industry. So basically, after that, we have to go back to see that if we can find some evidence for this, for example, variable to be included or excluded. And if we could not find anything there, then there is something wrong here. Okay, the model is not approving our model. So this kind of analysis is not approving our model, and maybe there is something wrong there. We have to go and investigate more to find the problem, or maybe we have to change our data, or maybe we have to change our sample size or the variables that we gather for our analysis. All of these factors can play a role in finding a kind of conclusion. And if there is something wrong there, we have to go and investigate that what the problem is and try to solve the problem.
Okay, so if this drops very much this weight, it doesn't mean definitively that we should omit.
Exactly.
Okay, so now this part is for Afshin, because I confess I still don't understand it enough to explain. Afshin?
Can you see my screen?
Yes.
All right, thank you, Anna, for your presentation. You gave us a lot of information, very informative points, and there are the important parts of this section. And I want now only to review some parts here, a kind of summary and important points that maybe it's not included in this presentation. So basically we faced with some questions, and guys, please interrupt me whenever you want, okay? And put your questions or discuss something that you like. So this discussion is free from now. So basically, what is the PCA? PCA falls under the category of unsupervised learning methods, and it comes from statistics. And the PCA is a way that we summarize somehow the variables that we want to put in our model. So it is for high dimensional systems that we want to make a smaller number of dimensions, and this is important for our analysis. Sometimes we have to do it because the problem that we are going to solve should be, for example, depicted on a chart, and in chart we have only 3 dimensions. And if we have more than 3 dimensions, we can not show it on a chart, for example. Okay, we have this situation in the finance, for example, for the interest rate and for the yield curve. For this kind of analysis, sometimes we want to make a model that we have to have only 3 dimensions. And the PCA can help us to summarize all variables that we have in our model to only 3 dimensions and 3 variables that we can work with. The second question is how we can do it by exploiting correlations between the system variables. So here the correlations is important, and we basically investigate the relation between the variables and try to summarize the variables that they are related to each other to one factor. And do we lose the accuracy? That's a very important question that not significantly is the answer. And the degree of accuracy will remain reasonable. What do we mean when we say reasonable? When we are losing some accuracy, even if it is not significant, we are losing some accuracy. So that should be important for us because we want our model to be as best as it can. But basically, this is a cost and benefit. okay? That we lose some accuracy, but we get some more information from the factors that we have, but with less variables, with less factors. For example, there we had 8 variables, but after factor analysis, we got only 3 or 4 factors. And why it is important? Because the variables that we put in our model needs data, and data is asset for us. You can consider the number of the variables and the amount of data that we have in our model as the degrees of freedom. The degrees of freedom is equivalent to the memory concept in computer science. And in computer science, we said that memory is very important for us. We want to use our memory perfectly and efficiently, okay? And if we want to do it in statistics, the equivalent is degrees of freedom. And the degrees of freedom is related to the number of the observations minus the number of variables in our model. So if the number of variables is higher, it means that the degrees of freedom is lower, and it means that the memory that we have is lower. Because of that, we need to make a good degrees of freedom for our model to have the higher accuracy. So sometimes the PCA is not only removing some redundant information from our model, but also it can help us to make a better model. And another concept that we face with some questions in this regard is about the standardization and normalization. That what is the standardization and normalization, and what is the difference between these two? The standardization is calculating some new variables by subtracting the mean and dividing it to the standard deviation. So this is somehow rescale the data to have a mean of 0 and the standard deviation of 1. But for normalization, typically we means that rescale the value into a range only between 0 and 1. So there, mainly we want to make the mean to 0 and the standard deviation to 1 and rescale the data and make the new variables scale free. But in the second one, we also do the same, but only we try to make a range between 0 and 1. But there are some points about normalization that we should take care. When data are seen as vector, normalization means transforming the vector so that it has unit norm. And the unit norm, you know that what does it mean in the vector computations. And also when data are random variables are about the random variables, and we have some random variables that we have seen some observations from them, normalization means transforming to normal distribution because there we have the probability. And for random variables, normalization means that we get close to the normal distribution. And the meaning you see, it's a little bit different when we are talking about only vectors. And then we have the third one, that when the data are hypothesized to be normal, normalization means that transforming to unit variance. It means that we have a kind of normal distribution, but the variance is not 1, and we want to make some changes, but the variance be 1. So normalization in different concepts and in different literatures has a little bit different meaning that we have to consider when we are talking about normalization. But standardization is something unique that we can see it here. And what is the use of this? The normality of the data is necessary if you need to do a statistical inference based on the PCA. So if you are going to use the PCA and you want to make some statistical inference, it's important to have the normality assumption. But if you don't want it, and as the data miner most of the time we don't need to make some inference, and we only want to make a model to make some predictions to get some values for the future. So in this case, we don't need the normality assumptions, and the PCA needs only a standardization. And this is essential for PCA. So keep it into your mind that the PCA needs a standardizing, even if we don't want normality in our model. Okay, so these are some points that we can think about. These are very important. The first one is that components are representative of the set of correlated variables that Anna described it very well, and they are interpretable. So sometimes the people say that because the components are a combination of different variables, then we cannot anymore interpret them, or we cannot get some meaning of them in our model. But it is not really true. As we have seen in the example that Anna described, we could finally interpret that this component is mostly related to the geographic part. That component is mostly about the age of the house. This component is mostly about the situation of the house. So we can make some interpretation. And also keep it in mind that the variables that they are in the factors, they are all highly correlated. So if we have some highly correlated variables in one factor, then that factor or component is a representative for all of them. So if we find that factor in our model meaningful, or we find that factor in our model very important factor, it means that all of those variables are very important for our study, because those variables are highly correlated to each other, and they are highly correlated to the factor also. So if the factor is important, those variables are important. So sometimes you hear that the people say in PCA, you lose the interpretability. It's somehow true, but not completely as the people imagine, because they think that, oh, if I use the PCA, I lose interpretability and I cannot say anything about my model anymore. But it's not true. If we have a factor in our model or a principal component in our model as an important component, it means that all of those variables that they are related to that component, all of those are important. So this is the first one. The second one is that the PCA needs standardizing the variables that I discussed it. So don't forget. And the third one is about the target variable. Don't put your target variable in PCA analysis, okay? So if you are doing the supervised learning, you have to keep target variable out of your PCA analysis. Another important point is about the amount of lost information that is not equal to the lost amount of variance for neglected factors. So if we put aside some factors, we put aside some components, and they have, for example, 20% of the variance, it doesn't mean that we are losing 20% of information from our model because of those noise that I told you during the presentation. So because there is always noise in the data, and the removed factors are mostly included the most noisy variables and most noisy part of the data. So it is the amount of the information that we are losing is less than the proportion of the variance that we are neglecting from our model. And the last one is sometimes we have to use graphical tools to solve a problem, and we have only 3 dimensions. So as I described, for example, in finance, we have some situations that we have to talk about the yield curve, for example, modeling, and we use the PCA to decrease the dimension to 3, that we can put it in our analysis and get some conclusions. And here we have some handouts. So the component weight, remember that it's greater than plus 0.5 and less than minus 0.5. So these component weights are important. The mutually exclusive components that I described is important. So we try to get to components that they are mutually exclusive. The reasonable variance means more information. So if we don't have variance, it means that there is no information. If we have no variance, what does it mean? It means that we have only one point. For one value, the variance is 0 because there is no variety in the value. All of the numbers are equal to one value. Okay, so there is no information there. If we observe it once, we have everything. We have future, we have past, we have now, and there is no question there. But when we have the variance, it means that we have some information. And because of that, the variance is important, and PCA is working on variance. So one question is that why PCA is working on variance, why the variance is important. Because the variance is somehow equivalent to the amount of the information. And if we can cover the variance, we are covering mostly the whole of the information that we have in our model. And the data is value. More variables in the model, more data is needed. So if we want to have more variables, we have to have more data and more costs, because gathering the data is costly. The data is there, it's true, we have in the big data area, and big data era nowadays is making facilities for some analysis, but those kind of information also cost something for the data provider. And PCA help us to keep more money in our pocket. Why? Because it means removing costly redundant variables from our model. If you need maximum interpretability, use PCA carefully. We can interpret about our variables, we can interpret something about our model, all of them are true, but the maximum interpretability, if it's our goal, the maximum one, then the PCA is losing some of the variance from our model, and maybe we don't want to do that. We want to keep all of the variables in our model, and the only thing that we need is a good prediction for the future. We don't need to have a good model. We don't want to make a kind of inference about the variables and their relations with our response. We only want to predict. If this is our goal, then the PCA is losing something, even if it is 10% or less than 10%. And the next one is that if you need maximum performance in your model, take the first principal component and initial features and feed the model. So this is a trick. If you want the maximum performance, one way for you is that take the first principal component, calculate it, take it, and then with the other features in your model, put all of them in your model, okay? And then try to see that if the criteria that they remove the redundant information, remove the first principal component or no. If it doesn't remove it, then maybe remove some other variables with less information and keep the first principal component in the model, and you will see that the accuracy of your model will increase dramatically. So this is a kind of trick that you can use it. It's not only about the first principal component. You can also take all of the principal components and then combine them with your initial features and then try to make your model. And the other point is that factor analysis. If you are interested, you can go to this address and see one SEM customer loyalty model that I provided there for you. Okay, guys, any question by now?
One question about the last handout that you gave. Not the factor analysis, but the other one. Do you mean that we can take the first principal component and initial features are the variables that we already had?
Exactly.
But even the ones that are inside that explain the first component, or not those ones?
They can be. They can be. So we don't care. We only make the principal components and then we combine them with the features, with the variables that we initially have. Okay. And then we put all of them in our model to see, and we give this opportunity to the model to choose the best of them. So sometimes it finds that the combination of the variables is somehow more informative than the initial features. And it removes the initial features, but keep the components that we import.
Oh, you mean we do a model with the first component and then compare it to another model with the features?
No.
No?
I mean that we combine all of them, okay, in a data set. And then we put all of these variables as the explanatory variables.
Oh.
And then
Okay.
make the model and give this opportunity to the model to select the best one.
Okay.
This is somehow the way that the neural network is working. You know what the neural network does?
We have not get that. We didn't get that yet. There yet.
Yes, but this is the same, because neural network do the combination of the somehow it makes a kind of combination of the initial features and try to test all of the combinations that is possible for the initial features and candidate them as an input to the model. And because of that, we need high performance computational power. Because we need a lot of calculations, we need a lot of combinations. All of the combinations between the initial features should be tested, right? So it needs a lot of computation, and the computation power is a matter here. And because of that, they said that the neural network is very expensive in computation, because it tests all of the possibilities. And PCA is somehow very simple part of that. It makes a combination of the variables and then we can input it. But if we have the computational power, why we don't use the neural network? It's a good question. So the neural network nowadays is a substitute to this strategy, but in the past that we didn't have this neural network, this kind of strategies and tricks was working.
Okay. Mm-hmm.